and welcome to this video on EDEXCEL Topic 1, Atomic Structure and the Periodic Table. My name is Chris Harris and I'm from AlleryTutors.com, and basically the whole point of this video is to go through an overview of Topic 1 for Year 1 for EDEXCEL. Now, the slides that I'm using here, you can purchase them. They're great value, great for revision, an alternative to books. And they summarize the content for EDEXCEL as well. If you'd like to purchase them, you can click on the link in the description box and you can get a hold of them there. But like I say, this is linked to the EDEXCEL specification, and obviously the specification points are listed on here for Topic 1. So if you're studying EDEXCEL chemistry, A-level chemistry, then this should be perfect for you. Okay, right, so we're going to start with looking at the structure of the atom. So the atom is made up of a nucleus. The nucleus contains neutrons and protons. It's very small, not very big at all. And the electrons whiz around in shells on the outside of the atom. In terms of the structure of these, the relative charge of protons is +1. The mass is 1. For neutron, it's neutral, so it has no charge. Relative mass is 1, same as a proton. Electrons are negatively charged, so they have a charge of -1, and their relative mass is 1/2000. So you can't put no mass, you have to put some mass, because electrons do have a mass. Okay, just looking at the element, obviously in the periodic table, the top number, or the bigger number, because it might be on the bottom in some periodic tables, the bigger number is the mass number. It tells you the number of protons and electrons in the nucleus. The small number tells you the number of protons. It's called the atomic number. And obviously in atoms, the number of protons equals the number of electrons as well. Okay, so let's look at some ions and isotopes. So ions have a different number of electrons and protons. So we've got here the negative ions have obviously gained 2 electrons. In this case, this is for oxygen, and they've done that to gain a full shell of electrons. And you can see here we've got 8 protons. With a charge of +8, 8 neutrons with a charge of 0, and the number of electrons is 10, so it's gained 2 extra ones from the normal 8 that it has. And if we add all them numbers up, we should get a total charge of -2, and obviously this is a negatively charged ion. And this would be attracted to a positive ion, and this was what makes them stable. Positive ions obviously lost an electron to form a positive charge. The number of protons in this one, in this case, is 11, so charge of +11. 12 neutrons in this case for sodium, but they have a charge of 0. It's lost an electron, so it only has 10 electrons instead of the 11 it would normally have as an atom. So if we add all them numbers up, we should get a total charge of +1. So obviously these would combine together to form a compound, which is what makes them stable. Okay, it's the formation of compounds that do that. Okay, isotopes are basically elements with the same number of protons but a different number of neutrons. So you can see here we've got 3 carbon examples. These are all isotopes of each other, and you can see that we've got 6 protons. They've all got the same number of protons, but they've got a different number of neutrons. And you can see that obviously the carbon on the left here has 6 neutrons, 7 neutrons in this one, 8 neutrons in this one. That's why the mass number is increasing at the top there. Okay, make sure you know your definitions as well. The relative atomic mass is the weighted mean mass of an atom of an element compared to 1/12 of the mass of an atom of carbon-12. Must remember that. And the relative isotopic mass is basically the mass of an atom of an isotope compared to 1/12 of the mass of an atom of carbon-12. Relative molecular mass is down here as well. You don't need to know this one for EDEXCEL, but it's just useful to kind of compare it with the other two as well. Okay, so mass spectra is a great way in which we can identify an element from its isotopes. So just going to give you a bit too around the graph here, and you can see the bottom axis is the mass to charge, or MZ as it's also known as. This is basically the mass of an isotope divided by its charge. So most have a charge of +1, so effectively this is just the same as the isotopic mass. So the MZ is the same as that. Some ions can have a double charge, in which case it obviously halves the normal value because it's mass divided by 2 if it's a double charge. Alongside its percentage abundance, it's always shown on the left-hand side of the axis. It can be shown as a percentage or as a nominal value. It depends. You've got to be vigilant with that and have a look. But if it's a percentage abundance, obviously all the isotope abundances must add up to 100%. So in this case it does, because you've got 75% and 25%. Okay, this spectra, it shows two isotopes of one element. So there are 75% of the isotopes with a mass of 35. And we've got 25% of the isotopes with a mass of 37, as you can see here. So this is assuming that they have a 1 plus charge. If they have a double charge, this will halve this amount, but that's most of them do have a single positive charge. Okay, and so from this we can work out the relative atomic mass, which is what we're going to look at now. Okay, so the relative atomic mass can be calculated using the abundance of A, which is the master charge of A. So abundance of isotope A times by the master charge of A plus the abundance of B times by the master charge of B, etc., depending on how many isotopes we've got. Because we've got two of them here, this is obviously suffice. Divided by the total abundance, in this case it's percentage abundance, so it'll be out of 100, but if it's not percentage, make sure you add up the total abundances that you've got and add them up and divide them there. Okay, so in this case, 75 times 3, 75 times 35, sorry, and we've got 25%, so it's 25 times 37 for this one. Add them two up, divide by 100 because your total abundance is 100, and that gives us a relative atomic mass of 35.5. So in this case, if you look in the periodic table, the element for this spectrum here is chlorine. We can also work it out using tables as well. Obviously, we've used a graph there, but we can use a table. So we've got an isotope here, the master charge isotope, of various isotopes. Here we've got 5 isotopes making up this element. And we've given the relative abundances of each isotope. So again, using this formula here, we can work out the relative atomic mass. So all we do is we do 70 times by 20.5, 72 times 27.4, and so on. And we keep multiplying them. And we add them up individually, as you can see here. Then we divide it by 100 because it's the abundance is a percentage, so it's always out of 100. And we should get the answer is 72.6. And if you look in the periodic table, this should point to germanium. So it's really good for obviously identifying these elements, like I say. So make sure you have your periodic table handy for this type of stuff. Okay. So we need to know how we can calculate isotopic mass as well. So let's say we've got potassium. It has an AR of 39.1 and we've got to calculate the isotopic mass of an isotope with an abundance of 5.788% and other isotopes being potassium 39, which is 94.20%, and potassium 40 being 0.012%. So this is a bit different because actually we've been given the relative atomic mass and we've got to calculate the isotopic mass. So this is a bit tricky. You'd be alright with this if you do maths, you probably look familiar with it, but there's a bit of maths here, so just to warn you. Okay, so let's look at our formula here first. So we're using the same formula as we've seen before: abundance of A, MZ of A, abundance of B, MZ of B, abundance of C, MZ of C, because remember we've got 3 isotopes here. And you can see that we've got a total abundance obviously on the bottom, and the total abundance is obviously going to be out of 100 because it's all percentages. So what we're going to do is we're going to put our numbers in here. So we know the relative atomic mass is 39.1. We know 94.20 times 39, and we know the 0.012 times 40, because obviously that's the isotopic mass. We know the percentage of this one, but we don't know what its abundance is. We don't know what the mass is of this isotope, and that's what we want to work out, which is I've represented that with a big red X there. Okay, divided by 100. Okay, so this is where the mathsy bit comes in. So what I've done is we've basically multiplied these two out, and we've basically got a grand total here of 36.74.28 plus, and then we've left this bit here divided by 100. So all I've done is just sorted this little bit out here and simplified it. Then what we do is we then multiply both sides by 100, because if we've got divide by 100 here, then to get rid of the divide by 100, we multiply that side by 100, and it effectively gets rid of that. We multiply that side by 100. So we get 3910 on this side, and effectively we get rid of the divide by 100 here. Then once we've done that, we then drag this number here across over to this side, and when we go across the equal sign, we subtract. So it's 3910 minus 3674.28 equals 5.788x. So you can see it's a bit of algebra here. Obviously, if we do this sum, we should get 235.72. That equals 5.788x. Remember, this is the bit we want to work out. And this is where the magic happens. So we rearrange this. We want to get x on its own. So what we need to do is divide both sides by 5.788 to get rid of this bit here. So divide by that number, that cancels that out. Divide this side by the same number, because whatever you do to one side, you've got to do to the other. So it's 235.72 divided by 5.788, and that should give us x as a value of 40.7. So if we round that up to the nearest whole number, that's 41, because isotopes must have a whole number mass. That's why it's whole number. So make sure you do that. So the answer to this one is 41, and there's quite a few marks available there. So, but if you follow the method, you know how to do it, you should be fine. Okay, predicting mass spectra. So oxygen is made from two isotopes. Okay, so we've got 98% abundance of oxygen 16 and 2% abundance of oxygen 18. We've got to predict the mass spectra for O2. Okay, so we've got 98% is basically 0.98 and 2% is 0.92. So what we're doing is writing the percentages as decimals. Then what we need to do is create a table showing the isotope combinations of them in a molecule of O2. And we're going to multiply the decimal form abundances of each isotope to get the relative abundance for each molecule. Alright, so what we're doing is we're looking at the different combinations. Remember, O2 is two lots of oxygen, but oxygen comes in two isotopes. We've got oxygen 16 and oxygen 18. So if we have two oxygen 16s bonded together, then what we do is we multiply the two decimal percentages of oxygen 16, and that gets that number. If we had an oxygen 18 and an oxygen 16, there's the bond there, look. So O1816, and we do the percentage of, or the decimal of the abundance of oxygen 18 times by 0.98, and we get this number. So basically what we're doing is we're multiplying all of the different combinations, and we're getting these numbers here. Then any molecules which are the same, we add the abundances up. So we see we've got oxygen 16 and 18, and 18 and 16 are actually the same. They're just obviously different way around, but in terms of the abundances, they are the same. So what we do is we do 0.0196 plus 0.0196. So these two here. So these add them up and we get 0.0392. So we're taking into account that. Then what we need to do is we need to divide all of the relative abundances worked out before by the smallest value. Now the smallest value here was 0.0004, okay, because it's quite rare this to get two of these together. And this will give you the whole number ratio, which can be used to predict your spectra. So you can see here, there's the molecule, oxygen 16 and 16, okay. This gives a mass of, obviously 16 plus 16 is 32, so we'll use that in a minute. But you see the relative abundance is 0.0604, that was for that one there, divided by the smallest number, which is that one, and that gives us a relative abundance of 2401. Remember, for this one, 16 and 18, we're using this number here because we've got two of them. We're taking into account both of them here. Divide that by the smallest number, we'll get 98. And then finally, the 18 and 18 one, we get 1 for this one because we're just dividing it by the smallest number. Okay, and then what we're doing is we're using these MRs here. These are your isotopes. Remember, the masses of your isotope, of your molecule, sorry. So we've got 13 here. So 32, sorry, here, which has got the relative abundance of 2401. We've got one at 34, which has got a relative abundance of 98. And we've got one at 36, which has got a relative abundance of 1. And that is basically how we predict the mass spectra from these molecules. Again, pretty tricky. Make sure you follow these methods here, and you should be fine. Okay, let's have a look at mass spectra of molecules. So again, we've got this abundance here on the left-hand side, shown as a percentage. So if it isn't a percentage, your isotopes must add up to 100. Just be careful, it might be a nominal value. And obviously we've got these MZs here, which is your obviously your mass to charge ratio, as we've shown before. And the peaks here, this shows the M+1 peak. So this is the molecular ion peak, and this is the same as the relative molecular mass of the molecule. So sometimes we get fragments that break up the molecule, and sometimes this isn't. So this is an unfragmented molecule, hasn't been broken up, and you just get this M+1 peak. So basically this is just the mass of the full molecule. Okay, right, electron configuration. So this is quite important, this bit. So we need to know about the different types of shells that we've got. So electron shells are split into 4 subshells. We've got an S subshell, it can hold 2 electrons. A P subshell has 3 orbitals, it can hold 6 electrons. The D subshell has 5 orbitals. It can hold 2 lots of 5, which is 10 electrons. And the F orbital has 7 orbitals and basically can hold 14 electrons. So I've color coded these. You can see them down here. So shell number 1 has a 1s orbital, which is there, and the number of electrons is 2. So we've got 2 electrons sitting in there. Shell number 2 also has a p orbital now. Remember, these p orbitals can have 2 electrons. Each orbital can hold 2 electrons, but we've got 3 of them. So we do 3 times 2. So it's 2 plus 3 times 2. It's 8 electrons in total. Third shell, we have a d orbital, and obviously if you can get the 3d subshell involved here, and the 3d subshell, again, each orbital can hold 2, but we've got 5 of them in total. 5 times 2 plus the p orbital electrons plus the s orbital, 18 in total. So as long as you know these different orbitals here. Okay, we need to know about the shape of these things as well. So the S has 1 orbital and it can hold 2 electrons, as we've discovered before. So the S orbital is spherical in shape, and the 2 electrons can move anywhere within this sphere. The P orbital has 3 orbitals, and each one can hold 2 electrons, and they've got these really classy names. So we've got the PX orbital, the PY orbital, and the PZ orbital. And you can see one's along the horizontal, one's vertical, and one is kind of going away from you. So it's like sticking out towards you. And we combine all these together. Obviously, all these are 90 degrees of each other as well. So in a 3-dimensional shape. But we can combine them all and we make the full P subshell. So we've got 3 orbitals, each holding 2 electrons each. And we combine them to form this shape here. And this is the P subshell. So there are 3 p orbitals in the shape of dumbbells, as you can see there, or figures of 8. They can hold 2 electrons and they can move anywhere, like I say, within this shape. Okay, you do have something called spin pairing as well. And so when 2 electrons occupy 1 orbital, what they do is they spin in opposite directions. You'll see some of these diagrams, these energy diagrams, with arrows representing electrons, and the arrows show which way it's spinning. But I'll show that later on. Okay, so we've got this electron configuration. Remember, we've got this very specific configuration that we write them out in. So basically, you write them out like this. This is an example of one. So the number in front of it tells you the shell number to which it belongs to. The letter tells you the subshell. So this is an S subshell. And the little number above it tells you the number of electrons that are in this shell. Okay, so the electron configuration for iron is this. So we've got 56 and 26 here. So this is the electron config. This is the element here that we're using. Now the electron configuration is 1s2, 2s2, and you can see we're filling them up. Remember I was talking about them arrows? This is showing the spin pairing of electrons. So fit 2 electrons in the 1s and 2 electrons in the 2s, but they're spinning in opposite directions. 2p6, 3s2, 3p6, 4s2, 3d10. Okay, so this is the electron configuration for iron. Now the crucial thing is you've got to check. Use these small numbers on the top and they should add up to give 26. Okay, so you're adding up all these. That's really, really important. This is showing how the electrons are arranged. You can see lowest energy is down here. This is the one closest to the nucleus. And as we go further up, we're getting further away from the nucleus and these are higher energy. So we fill from the lowest. And we fill orbitals singly first as well. So you can see here, these ones are all filled singly. Then we pair up if we have to. So this is due to electron repulsion. I kind of liken this to a bit like a bus. I don't know if you've ever been on a bus before where you've got, where it's reasonably full and you get people sitting on the individual seats. They put the bags next to them because they don't want anybody sitting next to them. You know, they like their own private space, which is fair enough. Electrons are a little bit like that. They will occupy an orbital. If there's a free one, they will sit on it first. And then only when all of these seats are full does then the electron start and have to sit next to somebody. It's a bit reluctant to do so because it repels, but it's a bit like that on buses. I know it seems a bit odd, but it's one of these bizarre observations I kind of make. So it's a little bit like what electrons do. So they fill singly first, then they pair up. Okay, so have a look at some ions. So with ions, you just add or remove electrons from the highest energy level first. Transition metals behave a little bit differently, but we'll look at that on the next slide. So the electron configuration for Ca2+, what it does is it loses 2 electrons from the 4s, okay, and you'll see it disappear here a little bit later on. So, but there they are there. It'll lose them ones, and it'll basically just have a full shell in the 3p and 3s. So there's the configuration, okay, and so what it's going to do is lose that 4s2, as you can see on there, and you can check if you add up all the numbers. You've got 2, 2, 6, 2, and 6. They should add up to be 20 minus 2, because calcium had 20 electrons. We've lost 2, so it should add up to 18. So just check and make sure that happens. So we lose from the 4s. There it goes. Okay, so it disappears, and that is now the energy level diagram for calcium 2+. Okay, let's have a look at them transition metals that we were talking about. Now, chromium and copper behave a little bit differently. So an electron from the 4s orbital moves into the 3d orbital to create a more stable half-full or full 3d subshell respectively. Okay, so for example, if we look at chromium, the electron configuration of chromium is actually this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Now, it's not this where you've got 4s2, 3d4. Okay, the electron in here would actually jump into this 3d and create a half-full d subshell, which is 3d5. So it's really unusual. Just make sure you look out for that. So they transition metal ions as well, they behave a little bit differently. So the electron configuration for Fe3+, what it does, it actually loses 3 electrons, which is fine, but 2 of them come from the 4s and 1 comes from the 3d. So we're not actually removing them from the all of them from the 3d orbital, even though the 3d is slightly higher in energy. So you can see here, here's the electron configuration. Okay, this is for iron. And then we remove the 3 electrons and we have 3d5, as you can see. And again, if we add all them numbers up, we should have 26. Iron did have 26 electrons. Take away 3, should be 23. So if we add up all these little numbers here, should get a total of 23. Okay, let's have a look. Lose them from the 4s first, then the 3d. Lose them there, and then we've got the 1 there. Okay, so 4s first, then the 3d. That's the key thing when we're removing electrons from transition metal ions. Or transition metal atoms, should I say, to form ions. Right, okay. Okay, so just obviously we know about these SPD blocks, we know about ionization and how the electrons are removed, but we need to know how that correlates to the periodic table, because you're going to be using the periodic table quite a bit, obviously. So the group number relates to the number of electrons in the outer shell. So for example, group 2 elements have 2 electrons in their outer shell. These blocks here, the ones in red, are also known as your S block elements. So that includes group 2, for example. The green ones here, these elements are also known as P block elements, okay, because they contain their outermost electron in the P orbitals. These ones are known as D block elements, so these are the ones in the middle here. Some of them are transition metals, not all of them, but most of them. These blue ones down here, these are called F block elements, so these are the ones which are really big elements. So uranium's down there, and americium, etc. Okay, right, let's look at the electromagnetic spectrum, because we're going to look at about the electron shell and look for the evidence for a shell structure. Okay, so this bit's going to be quite tricky, so listen carefully. Right, we've got this electromagnetic spectrum, okay, and you might have seen this in physics, if you do physics, of course. But the electromagnetic spectrum shows the types of radiation at different frequencies, okay. So we have, you might have remembered maybe Richard... not Richard of York gave battle in vain, that's the colours for just the visible light bit. You might have known that bit anyway. Richard of York gave battle in vain. It tells you the order of the visible light. But you might have got a mnemonic that basically helps you to remember the order of this. Radio waves down here, lowest energy, all the way up to gamma rays, which have the highest energy. So yeah, increase in energy and the frequency as well. So the waves are much squashed here, shorter wavelength. Along here, and obviously the frequency is increased as we go along to gamma rays. So atoms then, what's it got to do with atoms? So atoms can release energy named in the electromagnetic spectrum, and basically we're going to say how that happens. So atoms can be very strange things at times. Okay, we're going to look at something called an emission spectra, okay? And we look at something called line spectra. And this is a way of identifying elements and is evidence for quantum shells, okay? So quantum shells, remember that word, you're going to hear it quite a bit. Okay, so an atom, or the atom, has shells, okay, and we know them as quantum shells, okay, or energy levels. And we've got a diagram here showing 3 different energy levels. So this is known as ground state, the one at the bottom, and it's the shell closest to the nucleus, so we call that n equals 1. So they have discrete energy values, and the electrons can move from one quantum shell to another quantum shell, but they can't exist in between. So when an electron absorbs energy, there it goes, okay, it moves up to a higher energy quantum, or a higher quantum shell, okay, and this electron is effectively being excited, okay. Yes, but you never heard about that, electrons being excited, but yes, they can get excited. Okay, so if they absorb some of this, some energy, eventually though, the electron will move back down and release some of this energy. So it moves back down to an energy level. Now it could fall back to the same one that it came from, which is N2, could go back to N equals 1, okay? And obviously we can actually identify where this electron might have landed, where it's hit. We'll have a look at that later on. Okay, so we get this line spectra, or we call it an emission spectrum, okay, which is the frequency of light given out when an electron moves down energy levels, okay, and we see them as coloured bands, which looks really, really pretty. It looks a bit like a barcode, okay, and you can see all these different coloured bands here, so red ones over here, and your violets and purples over here. So every element has a different electron configuration, and so will absorb and emit different frequency of radiation. So the emission spectra is unique to different elements. Now this is brilliant. It is literally like a barcode. If you go into the supermarket, got a barcode on a product, that barcode is unique to that product. So when it's scanned at the checkout, the right price comes out, and obviously the right item comes up as well. So it is literally like a barcode for an element. Okay, so it is unique. So the lines on an emission spectrum show the electrons moving to different energy levels, okay? And I'm going to show you using this energy level diagram here, or quantum shell diagram, okay? So emission spectra show lines in different regions of the electromagnetic spectrum, okay? So we call this a group of lines a series. So series of lines are created when electrons move to the same energy level from different ones, okay? So let's have a look at some examples here. So the lines get closer together as the energy and frequency increases, okay? So remember, this is the bit where the energy and frequency is the bit where we've got UV and gamma and X-rays. They're the really high energy frequency ones, remember from that diagram. So let's have a look. So you see we've got these yellow ones here, okay? So basically the arrows here are showing the potential path an excited electron. Remember, the electron's already been excited, could follow to different energy levels in a hydrogen atom. So you can see this one's moving down here, this one's moving from a level slightly lower, this one's moving exactly. So it's going all the way down to ground state, which is n equals 1. Now electrons which fall into the ground state, which is n equals 1, they produce a series of lines in the ultraviolet part of the spectrum. Okay, so I'm just going to go back and just watch how these arrows correspond to the bands in your line spectra, okay? So I'm just going to go back and then just have a look. Okay, so you can see this one here that's travelled the shortest distance has a band that's very spaced out here. It's got this very thick band here, whereas the ones like here, because they travel in a very similar distance, the gap between them isn't as great. Then they bunch up really close together and they're a little bit thinner. But again, these ones here, you need to know that if they fall to ground state, they form in the ultraviolet part of the spectrum. Now I'm going to show you what happens when they fall to n equals 2, and they'll form a little bit further over. So watch this. Okay, so you can see the bands correspond to these. So we've got the electrons which fall in the second energy level, which is the n equals 2. They produce a series of lines in the visible part of the spectrum, and you can see them there. Notice we don't have as many bands as we did here because we're not going down to the n equals 1 banding here, so we've got less arrows dropping. And if we go to the n equals 3, we get bands appearing in the infrared bit. Okay, so you can see here they appear in the infrared part of the spectrum, and there's the banding there. Okay, so make sure you're able to identify, depending on where the electrons are dropping to, which part of the EM spectrum you will see these bands form. Okay, so how does this link with evidence for quantum shells? Well, emission spectra is evidence to prove the existence of these shells. So the radiation emitted will have a fixed frequency, okay, as the energy of these shells is fixed. Okay, remember, we can't have the electron hovering between these shells. So they can only exist in these very specific shells. They can't be in between, like I say. Each shell has a fixed energy. There's a fixed amount of energy. We call this quantization or quantum chemistry. Sounds very grand, doesn't it? Okay, the electromagnetic radiation is absorbed, remember, to move the electrons to higher energy shells. Remember seeing that in 2 slides ago. And it's emitted when they drop to lower ones. And so what we get is these defined lines, very discrete lines. There's no blurriness to them. They're very defined, crisp lines as we go across the spectrum. Okay, and this proves that electrons can only exist in shells. They can never exist in between them. So we get this nice defined spectrum here. Okay, no ambiguity, nice clean lines. So that's proof that we actually do have a quantum atom and it's shell-based theory. So this is proof of that. Okay, now we're going to look at some trends now to do with these. Now we've proved this shell model. We're going to look at other bits of evidence which could look at that. And the first one is ionization. So ionization energy is the minimum amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. You must remember these key things, especially the bits underlined there. Okay, so this is an equation to show an ionization of sodium. So notice the gaseous state. Okay, sodium gas, Na plus gas. The first ionization is plus 495.8 kilojoules per mole. This is an endothermic process. Energy is needed to remove that electron. Always include your state symbols. And obviously, like I say, it requires energy. Positive value all the time. It's endothermic. So we need to consider some things when we're talking about ionization. Okay, so we've got shielding. And basically, the more electron shells between the positive nucleus and the negative electron that has been removed, which will be in the outer shell, the less energy is required. We've got this weaker attraction. So shielding you'll see quite a lot, and you're going to use this word quite a bit as well. The atomic size, the bigger the atom, the further away that electron is, the outer electron, from the nucleus. So that means the attractive force between the nucleus and the outer electron is reduced, and therefore it's easier to remove that electron. Okay, so these are all factors which will determine how much energy is needed to remove that electron, which we call ionization. And obviously nuclear charge. The more protons in the nucleus, the bigger the attraction is between the nucleus and the outer electron. This means that we need more energy required to remove that electron, and so therefore it's have a higher ionization energy for atoms with a larger positive charge. Okay, so let's look at some trends. And we're going to look at groups first. Now, this is a graph showing the first ionization energy in group 2. But as we go down a group, the ionization energy decreases. Okay, and the reason why is because the atomic radius increases as we go down the group. The outer electrons are further from the nucleus and the attractive force is a lot weaker. So energy is required to remove an electron is actually less. It decreases because the atom is getting bigger. So it's about this size of the atom here, increased radius. And not only that, I told you this word shielding is going to come up quite a bit. The shielding increases as well as we go down the group. We have more shells between the positive nucleus and the outer electron. So shielding is increased. That means energy required to remove that electron decreases. Less energy is needed. And this actually provides strong evidence for shells and atoms, just like the line spectra. So it's more evidence to prove this. Okay, so let's look at successive ionization energies. So basically this is just the removal of one or more electrons from the same atom. So we just keep removing electrons from the same thing. And we call this successive ionization energy. Now, you can see here on the graph, we've got the successive ionization energy for magnesium. So basically we take a magnesium atom, we just keep removing all of its electrons. It's got 12 electrons in total. Now I'm going to use the energy level diagram you can see on the left there to basically try and explain it. So here's the ionization. This is the second ionization energy for magnesium. So we've got Mg plus will form Mg2 plus an electron. Now this is the ionization value of it. It's endothermic, so it's positive. Notice these jumps. We've got a jump in energy as we're moving electrons from the shell much closer to the nucleus, and you're going to see how this forms here. Okay, so let's start removing some electrons from this thing. Okay, we've got a general increase in energy because we're removing an electron from something that's increasingly more positive. Okay, so obviously removing an electron from an Mg plus is going to need more energy than removing an electron from just Mg, because this is already positively charged. So it's going to really pull that electron in, and it's going to get increasingly more difficult to do so. Okay, so the first set of electrons are the ones which are furthest away from the nucleus. These ones require the least amount of energy because they're obviously further, you've got more shielding, etc. So these are the ones in the 3s orbital. The next 8 are the ones in the second shell, so that includes the 2s and the 2p subshell. These ones require more energy because they are much closer to the nucleus, and also you're removing it from something that's increasingly more positive. So the shielding is less, and obviously it's getting increasingly more positive. So we've got this increase here, but that's the reason for this jump. And the next jump over here is removing the last 2 electrons, which are really close to the nucleus. This is going to be incredibly difficult to do. You need so much energy to do this, but there is this big jump because you're removing them from a shell which is much closer to the nucleus. Okay, so we know this is magnesium. Look at the number at the bottom. It's got 12 electrons. So look out for these little clues. Okay, so let's go back to this modern periodic table again. Okay, so the elements are ordered by proton number, not mass number. Okay, this is very important because we're talking about periodicity here. This is the trend, so we need to know about the periodic table. So proton number, not mass number. Okay, very important. The groups are columns, and basically elements in the same group have the same number of electrons in the outer shell. So, for example, in group 1, they would all have 1 electron in the outer shell. So the group number relates to the number of electrons. Like I say, for group 2, we have 2 electrons in the outer shell. And elements in the same group, they have similar properties. So for example, group 1 elements all react with water with increase in vigor as we go down the group, so they become more reactive. You might see these when you put them in these big water troughs, you chuck them in and they really react quite vigorously, produce lots of hydrogen gas, and some of them catch fire as well. So your likes of your potassium could even catch fire. Periods, these are rows, so these go across, hence the word periodic table. And elements in the same period have the same number of electron shells. So all these ones, for example, across here, they all have the same number of electron shells. That's the 3rd shell there. Okay, so these ones are known as S block elements. As we've said before, these ones are known as P block, these ones are known as D, and these ones are known as F, as you've seen just before. So as long as you're familiar with these blocks, that's really important. Okay, so we're going to look at atomic radii, okay, using the periodic table that we've seen. So as we go across period 3, the atomic radius decreases. As you can see, look, they're getting smaller and smaller and smaller. And you can see here's the graph showing this trend here. Now this is the atomic radius in nanometers. Remember, these things are really small, but you can see this general decrease as we go down. The reason why is because we've got this increased nuclear charge. Remember, as you go across the period, we've got more protons. And so what this does is this pulls the outer shell of electrons further in towards the nucleus and obviously hugs that a little bit, just a fraction, and makes it a little bit smaller. But crucially, the extra electrons elements gain across the period go into the same shell. Okay, so you've got to make that comment. You've got to say, look, they're going into the same shell. The shielding effect is similar. Okay, so we need to mention that as well. There's no good just writing, oh, you got more protons. You need to be talking about shielding as well. Okay, so make sure you've got both of them aspects in there when talking about it. Okay, the atomic radius increases down groups though, because we've got that extra electron shell added, so it gets significantly bigger each element as we go down a group. Okay, so let's look at the ionization in periods this time. Okay, so the ionization energy increases as we go across a period. So generally, as we go across a period, there's an increase in number of protons in the nucleus, as we've just seen. This increases that nuclear attraction. Okay, so we generally have this increase. Shielding is similar, like we've just seen before, and the distance from the nucleus marginally decreases. We've got more energies needed then to remove this outer electron, and the ionization energy decreases as we go across the period. But we do have these little blips, and you can see with aluminium and sulfur. So we need to try and explain them as well, or look at them. Okay, it's a similar trend for period 2 as well. Okay, so we see we've got this decrease of aluminium, and this is evidence for atoms having subshells. So you can see here the outermost electron in aluminium sits in a higher energy subshell, slightly further away from the nucleus than the outer electron in magnesium. Okay, so let's have a look. There it is there, look. So aluminium has got that 3p1, its electrons in the p orbital. Magnesium obviously just has the 3s2. So the 3p, the electron in the 3p is slightly shielded from the 3s. There you go. So it's in the 3p subshell, and the magnesium has it in the 3s. And this trend is obviously similar for period 2, because they might ask you about period 2 as well. Okay, let's have a look at the dip at sulfur. This is a little bit trickier, but a decrease at sulfur is evidence for electron repulsion in an orbital. Remember we were talking about electron repulsion just before in that orbital. So phosphorus and sulfur, they both have outer electrons in the 3p orbital. Okay, so there's no extra shielding here, so it's all the same. But removing an electron from sulfur involves taking it from an orbital with 2 electrons in. And remember, they've got this electron repulsion. They don't want to be near each other, so they're not going to put up much of a resistance when you try and remove this electron from something where it's already paired. So if we look at the electron configuration for phosphorus, phosphorus doesn't have that paired electron, so there's no electron repulsion to kind of make it easier to remove that electron, whereas sulfur does. You've got this pairing of electrons, makes it easier to remove because of electron repulsion. Okay, and again, period 2, make sure you can familiarise yourself with that as well, because they might ask about period 2. Okay, let's have a look at some melting points. So the first 3 elements going across the period, sodium, magnesium and aluminium, they all have metallic bonding. And obviously the metallic structure for sodium looks like that. So we've got this 1+ charge for the sodium ion, and we've got 1 electron being delocalized, and obviously there's the attractive forces there. The metallic structure for magnesium, you've got a 2+ charge in the middle and 2 electrons which are floating around. And you can see them there, but we've got this slightly higher attractive force because we've got a bigger negative charge and a bigger positive charge, got a bigger electrostatic attraction between these, so therefore the melting point increases. Like I say, increase in positive charge, more delocalized electron, smaller ionic radius, means we have a stronger metallic bond. Make sure we can talk about all these things, especially the bits that are underlined. They're key points. Okay, again, look out for period 2 because it's the same trend. Right, let's have a look at silicon. This is like right at the top here. So silicon is the highest melting point, period 3. It has a giant covalent or macromolecular structure. Okay, looks a little bit like this. Loads of strong covalent bonds. They hold all these silicon atoms together. Loads of energy is needed to overcome these bonds. And so that's why it's got a really high melting point. Much higher than any of the other elements that's on that graph. Okay, so let's have a look at the next element. Phosphorus is a massive crash down to phosphorus now. So phosphorus has the formula P4, much lower melting point than silicon. It only has it's a weaker, simple molecular structure. All it has is it just has weaker London forces that hold these molecules together, and it doesn't take much energy to break them forces. And so that's why the melting point of phosphorus is much, much lower. Okay, simple molecular. It rises a little bit though for sulfur. Sulfur still, again, only has London forces, just like phosphorus, but because the molecule of sulfur is S8, it's slightly bigger than the phosphorus molecule here. And so because it's slightly bigger, the size of the London forces is bigger. And so this means it has a slightly higher melting point than phosphorus. Okay. And then if we look at chlorine, chlorine has the formula Cl2, just a slightly lower boiling point than sulfur. It's a simple molecular structure, again, just like phosphorus and sulfur, but because it's only Cl2, it's a smaller molecule, smaller London forces, and a lower melting point. And then poor old argon at the end there doesn't bond with anything. It's literally just an atom. It has a much lower boiling point and melting point. and it only exists itself. London forces are weaker. Again, we're talking about London forces, hence it has a lower melting point. Okay, and again, with all of these things, make sure you familiarise yourself with period 2 as well. And that's it. That is the summary for topic 1 for atomic structure and the periodic table for EDEXCEL. Please support this channel by subscribing. Every subscriber really does count. It's brilliant. We've got so many. You just click on the circle in the middle and you get all the up-to-date videos and anything that's updated, you can see it on there as well. Also, just a reminder that these videos, these slides are available to purchase. Great value. You can use them for revision, put them on your tablet, smartphone, etc. But you can purchase them. Just click on the link in the description box. But that's it now. Bye bye.